Okay, welcome to lecture 4, computer architecture. Today's lecture will be about arithmetic for computers. We'll just be going over instruction, execution, and phase. Okay. Number 1 over here, we'll be discussing binary number and their representations. Binary systems uses digits 0 to 1, and there are unsigned binary, which are non-negative integers, and also signed binaries, which are both positive and negative integers. The representations are signed magnitude, one's complement, two's complement, and excess. One's complement and two's complement is also used when wanting to convert from hexadecimal or binary or even decimal to one of the other. Over here on the side, we can see a binary number chart showing the numbers 1 through 10 and their binary numbers. Next, we're going over hexadecimal representations. As mentioned earlier, they're also used in a single way that you can also use them in conversion to decimal and binary. In hexadecimal, we have 0 to 9 and A to F. And they are converted into 4-bit binary. As for real number representations, we have two parts, which are fixed points and floating points. Floating points consist of two variables, which have a sign exponent and a mantissa. As for the fixed point, it consists of three components, which are the shared exponents, the first variable, and the second variable. The IEEE standard is the sign exponent signified, which falls under the floating point or a sign exponent mantissa. At the end of the day, that is the IEEE standard. Next, we have different adders. There are half adders, full adders, ripple carry adders, conditional sum adders, carry look ahead adders, and carry save adders. Over here to the right, we have an example of a half adder and a full adder. A full adder consists of one half adder. A half adder consists of two inputs, a carry and a sum. When both combined, we'll have two inputs, a carry, and that will give us an output of one carry and one sum. The only difference between a half input and a half adder and a full adder is that an adder has two inputs, whilst the full adder has three inputs, and one of them is a carry. As for the ripple carry adder, it's a simple but slows, and it also carries propagate thorough all bits. As for the conditional sum adder, it pre-computes sums assuming carries always 0 or 1. As for the look ahead adder, it reduces carry propagation delay, and the save adder it efficients the adding multiple numbers simultaneously. Next, over here we have different types of multipliers. We have a serial multiplier, a parallel multiplier, Booth's algorithm multiplier, an array multiplier, and a Wallace tree multiplier. Over here to our right, we have an example of a Wallace tree multiplier, which consists of full adders and half adders as seen. They all add up in the ending. The way that they work is that they have multiple adders between them, just like how you construct an equation where it's like a plus b in between parentheses multiplied by c plus d is the same way that a Wallace tree multiplier works. As for a serial multiplier, it multiplies one bit at a time. A parallel multiplier uses multiple adders for simultaneous operations. A Booth multiplier it reduces the number of subtractions and additions, and the array multiplier uses an array of adders for partial products. Okay. Next, over here we have different dividers. We have a basic division concept, a restoring division, a non-restoring division, an SRT division, and a Newton-Raphson division. A basic division is a dividend that consists of a quotient multiplied by the divisor plus the remainder, whereas the restoring division consists of a subtracting the divisor from the dividend and restoring it if negative. As for the non-restoring, it's the same as the restoring, but the only different thing is that it won't restore a value that is negative. An SRT division uses table lookups for partial remainders and quotients. Over here on the right side, there's an example of a SRT division. We can see over here also using an imaginary number in this case, um, which is used in an SRT division, and it consists of a um, normalization and two inputs, a multiplexer, a multiplier, and an adder or maybe a subtractor, um, depending on the concept used. Following up here, we have a number representation impact on memory. Three types of memory usages. There are integers, characters, and floating points. Each consist of different bits. The integer and the floating point both consist of 32 bits, whilst the character consists of 8 bits. The integer, as seen over here on the side, has a signed and unsigned parts, whereas the character has a char, signed char, and an unsigned char. As for the floating point, it has a float, a double, and a long double types. Okay, over here we're discussing the errors in number representations. There are precision, quantization error, overflow error, and rounding errors. Precisions, those are like the smallest possible quantizations, whereas the quantization errors are difference between real numbers and closest representable numbers. As for the overflow is when a number exceeds the representable range that it's given, and the rounding error happens when approximants and floating point are mistaken or cause an error. And over here to our right, we can see a overflow error and how it is different and how it exceeds the range that it's given, as it's given in both a negative and a positive number. A full summarization and normalization for this PowerPoint and lecture just falls down to binary and hex numbers, different representations and different conversions, real numbers, which fall under them, fixed point and floating point representations, as well as adders, multipliers, and dividers, which have various types with different complexities, and the impact of memory, where it represents effects of memory usage and its performance, as well as understanding the precision, quantization, overflow, and rounding errors in each number representation. That was it for today. Thank you so much and have a good day.